Yes, hello. I want to welcome you from my side as well. Um, I've seen in the participant list, so the most people I already know, but for those who do not know me, my name is Ferdinand Wickedal. I'm working for the Fva GmbH since beginning of this company. I'm worked for the development of the workbench since 2008, so even before the Fva GmbH started. And I do this half of the week, and the other half of the week I'm doing independent expertise on gearbox failure analysis. Okay, so I want to start with our short presentation for today. Topic is the local load capacity calculation, the Fva Workbench. I will talk about the influences which influence the load distribution on the tooth lengths, and then the calculation methods which are used to do this. Then I will talk a little bit about additional effects and how reliable these results are. And half of the presentation today will be a short, an online demo in the new version of the Fva Workbench, which we will release tomorrow. So for the presentation, I will leave the camera off, and before I talk about the load distribution, a few words about the new release of the Fva Workbench. From release to release, we try to improve the workbench to give you a valuable tool for the design of gearboxes. And in the last version, we have speed up the calculations. So for some calculations, we have a cut of the calculations up to 80%. And this makes the workbench a very efficient calculation tool. And in the last years, the digital twin comes into focus. So we are working very strongly on this. So we have now implemented calculation for nonlinear materials, for plastic gears. We have added some more detailed calculations, for example, taking into account the centrifugal forces and planetary gear stages. You can add additional masses if you want to calculate your eigenmodes and eigenfrequencies. And the overall scope for the workbench is to provide for you a detailed simulation software which is as fast as possible and as reliable as possible. And I'm very happy to announce that we have a new cooperation. We now cooperate with the company RVL, which also provides a very detailed calculation software, not only for gearboxes, but for transmissions as well. And here in the Fva Workbench, we are focusing, let's say, on the static calculation without the real dynamics in the transmission system. So we can provide the bearing lifetimes, the bearing loads, the safeties for the tooth lengths, for the shafts. And we can also calculate very exactly the frequencies which are excited in the gear meshes. So we have the exciting frequencies, and we can calculate the eigenfrequencies in the drivetrain because we have all the stiffnesses and all the masses also available within the workbench. But then our calculation scope stops, and then with this cooperation, we can export workbench model in the new Rex format, and RVL Excite will load this Rex model into their software, and then you can do a full dynamic analysis of the whole drivetrain. You can as well now calculate the critical frequencies, but you do not only get the frequencies, but you get all the dynamic loads which are excited when you are close to an eigenfrequency, and you get also the behavior of your housing, so which part of the housing vibrates in which frequency and so on. But starting with the main focus of for today, the local load distribution, I want to first recapitulate what are the basic influences on the local load distribution. When we are talking about the local load distribution, that's the picture here in the bottom of the slide. We are looking for the different pressure values or sliding velocities or temperatures on every point of the tooth length. But still, the most important influence factors are the design. So, for example, the bending of the shafts, the torsion of the shafts, the elastic deflections of the bearing, of the housing, and so on. So with these elastic deflections in the gearbox, you will have the most important influence factors on the phase load distribution and also on the local load distribution on the tooth length. Then the load, of course, is a big influence on the load distribution and the local load capacity of a gear mesh. So if you have a very low load, the tolerances have a high influence, and the higher the load gets, the lower is the influence of the tolerances, and the higher is the influence of the elastic deformations. Then, of course, the tooth form has an effect on the load and pressure distribution on the tooth lengths. And as I said, the quality, the tolerances of the gears itself and on the tolerances of the bearing boards in the housing, they have a big influence on the load distribution. And of course, also the tooth modifications, which with which you try to compensate all those influence factors. So these are the basic influences which makes it necessary to look very detailed on your local load distribution to get a good pressure distribution, so that you can have, for example, smaller gears with the same capacity as if you would not take into account those local load distributions. Then I have some slides about the calculation methods. So we start with the most simple calculation method. This is the method described in the standards in DIN 3990 or ISO 6336. And here the phase width is divided in different slices, and the different slices along the phase width are represented by springs, and the spring stiffness is calculated also according to the standard, and the spring stiffness is in the standard called the C gamma value, and each of these springs has the same stiffness value, and there is no influence of one spring to the other, so there's no shear influence along the phase width. And with this simplified model, you can calculate the load distribution based on a linear misalignment, and this gives you the value for the phase the phase load factor KH beta, which takes into account an uneven load distribution in the standardized load capacity calculation. Then talking about the C gamma value, the C gamma value was derived from a lot of calculations based on the formulas according to Weber-Banachek. So according to this method, you can see the tooth as it is a beam with a variable cross section along the tooth height, and therefore there are analytical solutions present to calculate all the deformation influences, the contact itself, the bending of the tooth, the shear deformation of the tooth, and the deformation of the wheel body where the tooth is connected to the wheel body. So this is not the whole wheel body, but just the connection area. And these formulas, according to Weber-Banachek, they have been the basic for the simplified formulas for C gamma in ISO or in the DIN calculation. And the next little bit more detailed method is that we still use the simplified slice model from DIN or ISO, where we have divided the face width in different slices, and also then we have then different springs along the face width. But the difference with the simplified ISO calculation is that we now calculate all the deformation in the system very detailed. So we take into account the real bending curve, the real torsion, influences from a second stage on the shaft, housing deformation, the real deformation of the bearings, and so on. And then we apply those very detailed calculated deviation values on the simplified stiffness model. And what we get out of these calculations is still a face load factor KH beta, which is very close to the method of the standard. So we can use this KH beta value directly for the load capacity calculation in the standards. And as we have now the real deformation of the gear teeth based on the influence factors I have talked about in one of the first slices, then with this calculation, we can also give a recommendation to achieve a good or constant load distribution along the face width. And then the next step is that we do not divide the face width into different slices with different springs, but we look on the local stiffnesses on the tooth flanks along the lines of contact. So every point on the tooth flank has a different stiffness depending on the position, if it's in the middle of the face width or if it's in the root or in the tip. So we can calculate now this local stiffnesses by different approaches. So in the workbench, we have an analytical approach, which is a plate model, where we look at the tooth as it would be a plate, and there are formulas based on the Weber-Banachek calculation and on the plate model according to Schmidt. This is the same analytical approach which is used in RECOR, and we have actually we have a project in the FVA where we compare the results of RECOR and the workbench, and the results are not only comparable, they are quite the same. So this approach gives you the same results as you would get it from the standalone RECOR program. And the other approach is a FE approach. For this, we use the calculation program Stirac from the University of Aachen. The RECOR program is from the University in Munich. And these two methods give us the local values, and then for calculating the load distribution along contact line, a so-called influence number calculation method is used. So what is done in this method, you apply a force on one point along the contact line, and then you calculate the deformations for every other point on the tooth flank or along the contact line, and you do this for every contact point. So then you get the deformation matrix, which takes into account the local deformations of the tooth flank along the face width and along the profile. And with this very detailed stiffness information, you can now again calculate the load distribution, but not only along the face width, but for every contact line. So here, this is represents the 3 contact lines. So we have the 3 local stiffness values, then we have the Hertzian contact, we have tooth modifications, and we have the same detailed information of the system deformation. So, and here, the main difference is that we have here the shear between the contact points along the face width taken into account. So if you apply a load on this position, all the other positions are deflected also. And again, we get as a result the local load distribution. Here, not only along the face width, but also along the profile. And we get a modification proposal to achieve a constant or a good load distribution, also not only along the face width, but for the whole tooth flank in profile and in lead direction. So if you use this most detailed calculation, you will get load distributions or pressure distributions which look like this for helical gears, for example. And then there are different effects which occur. So a very important effect is the influence of the radius of curvature. So even if you would have a constant load distribution along the profile and the face width, the pressure values will increase when you are going towards the root of the smaller gear, to the root of the pinion, because then the radiuses of curve, or the radii of curvature, are getting smaller towards the root of the pinion, and so you will get higher pressure values, although the load distribution will be constant. So this is one effect. But we even have much higher local pressure values at this position, and we have also high load peaks at the end of the contact, and this is due to the contact of the tip edges with the tooth flank. So this tip edge has a notch effect on the contact pressure values, and this notch effect leads to or may lead to very high local pressure values here. So and this you have to take into account when you design a gearbox, and you have to take measures to avoid those local load peaks. If you have a helical gear and you will not apply a sufficient tip relief on your teeth, then this will result in exactly these load peaks, and usually you will, or in many cases, you will get then triangular flaking, which starts at the contact position of the tip within the root of the driving gear. And then we have another effect, the effect of the short contact lines at the begin and the end of the mesh. So you see the contact lines are getting smaller and smaller when you are going to these edges at the begin and end of the mesh. And although these areas have a lower stiffness and they take a much lower force than the contact points within the face width, you have the load is divided along a very small contact line, and so the line load and therefore the pressure values can get very, very high. So that's more or less a singularity, and this leads to very high pressure values, which are concentrated at a very, very small area. So the question is, does these high pressure values really lead to a gear damage? Because you can imagine maybe due to plastic deformation at this position, or to some wear or some small pittings which you get at these edges, and then when outside of this area the load is not so high, then yeah, no bigger gear damages will start from these load peaks. But usually, so I would not recommend to use such a high load peak in a standardized capacity calculation for calculating the flank safety. And actually, there is no method to use such a pressure value in the standardized calculations for the load capacity of the tooth lengths according to DIN or to ISO. But the DIN working groups are working on that. So I think in the near future there will be a method to take into account these local pressure values also in a standardized load capacity calculation. So there are different effects which can occur when you do tooth modifications for your gear mesh. For example, if you apply end reliefs, the same will occur if you apply tip and root reliefs. If you apply very high values and you have here a sharp edge because you have a linear modification form and no tangential transition from the end or tip relief to the non-modified involute, then you have a sharp edge here, and this will lead to also a notch effect and to high load peaks now within the face width. So if you apply too high tip or end reliefs, you do not really avoid the high edge contact values. You only shift this high edge contact values more to the middle of the tooth flank. So for this, you have to have a quite good load distribution program, as for example the Fva Workbench, to take into account these influences, and then you can modify your tooth modifications, for example, by reducing the amount or by changing to a circular end or tip relief to avoid those local load peaks. And before I switch to our online demo for today, just two examples from real life, where I've calculated the local pressure values of tooth flanks for failed gearboxes. And here you see a highly overloaded gear stage with this pitting line in the foot root, and here's some scuffing in the tip, and this is also represented very good in the result of the Fva Workbench. We have here also this red line, and the foot root is just this position where also the pitting occurred due to the high pressure values. And another example, that's not pitting, but micro pitting. This is not yet a failed gear, but you see how accurate this method is. You see in the foot root a linear line which micro pitting, and here a small area also with micro pitting. This is due to the higher pressure values at these edges when you have not an optimized tooth modification. And after I've calculated the gearbox with the Fva Workbench, I see exactly the same distribution of the local micro-pitching safety as I've seen it in the real gearbox. So that's not only theoretical. The methods which are applied in the Fva Workbench, they have been used for, let's say, 40 years in the companies and in the FIA, and I think a lot of gearboxes which are manufactured in the last 40 years are in these gearboxes. The tooth modifications are evaluated with these methods, which are now integrated in the Fva Workbench. In the online demo, I want to show you how to calculate the phase load distribution and the phase load factor of the phase width. So this is the basic method for evaluating the tooth modification. Then I will go on to the local calculation of the load and pressures. I will evaluate tooth modification to achieve a good load distribution on the tooth length. Then I will calculate the micro-pitching safety and the local tooth root stresses as well. And if you are interested in the FEA or network, or in the what we do in the FEA Workbench, you can become a part of our network, and in all the social media, all of the social medias. Okay, but then let's switch to the FEA Workbench. And I will not set up a new model from scratch, so this is not the topic of today. I just have loaded in a predefined model, a two-stage gearbox, and I will focus on the input stage. And for looking at the load distribution, I just calculate the system calculation. System calculation calculates all the deformations in the gearbox, the shaft bending, shaft torsion, elastic bearing deflections, and so on. And then we can have a look at the result of this system calculation by double-clicking on the actual result snapshot. And then I have defined output report just for this webinar today. So we will not see all the calculation results which the Workbench produced, but just these values which are interesting for our webinar. So that is also very easy to achieve, to make your report templates where you can switch from one template which show you very detailed results, or to a template which show only the most important results. Okay, but how to define the reports? This is also another topic. So for the input stage, the Workbench calculates KH beta factor of 1.4, which is quite high. When we look at the diagram on the side of the load distribution, you will see which influence factors had led to this uneven load distribution. So the green area is the bending deflection of the shafts. Additionally to the misalignment, if the bearings have elastic or static deviations. And the blue curve is the torsion of the gear teeth. So for the pinion, because the pinion has a much smaller diameter than the gear wheel, we have also an effect due to the torsion, because the gear wheel is very stiff due to the high diameter. We have not so much influence of the torsion on the gear wheel. And then we have a linear misalignment of round about 17 micrometers, and the recommendation of the workbench is to remove 17 micrometers on the left of the tooth flank. So I will just do that, and for this I choose to implement a helix angle modification, and I've already filled in this value, so I will not fill in 17.1 but 17 micrometers, which is quite close. And then we do another system calculation, and then we compare these both results by setting the first calculation as reference and compare the second calculation with this reference. And then you see without this helix angle modification, we have a quite uneven load distribution. And now we have a much better load distribution along the face width. So we have a cage beta value of 1.02. And for those who are already working with the version 6.1 with the workbench, usually you have, this would be an iterative process to achieve a constant load distribution, because in the 6.1 we just calculate the load distribution, the deflections in the gearbox based on the actual uneven load distribution. Then we apply the tooth modifications, but now we have other deflections in the shafts and bearings, and so we have to adjust this tooth modifications a little bit. So this needs in the Fva Workbench one, two, or three iterations. In the actual version, the 7.0, you can go to the gearbox, and under control parameters, there's a switch which is called phase width modification proposal for uniform load distribution. And then this iteration is done internally automatically. So this takes a little bit more time, but you always, if you get with the first calculation, you get the recommendation for a real constant or real, let's say, symmetrical load distribution. So the next step would be usually that you apply an additional crowning to the gears to avoid high or harsh edge contact. In this case, I will not apply a lead crowning, but I will apply end relief on both sides. So I've decided to use a circular form, and amount of the end relief of 5 micrometers, and the length along the face width of 5 millimeters. So I just recalculate this variation and have a look at the results. And this is the load distribution we achieve now by applying this tooth modification. And yeah, it's still a quite low cage beta value. And I think with this results, we can go on and have a look at the local load distribution along the whole tooth flank. For this, I have to activate this local calculation as well. And yeah, I just add here not only the local load distribution, but also the gear force excitation and the temperature and micropitting calculation and the local root stresses. So this takes a little bit longer because the calculation of the tooth stresses is with boundary element method. So this takes a little bit longer than the analytical approaches. And then I have a look at the results we get from the local calculation. Again, the 2D calculation, and now we have the load distribution values. And although we have already applied end reliefs, we have still high load peaks at begin and end of the mesh where we have those short contact lines. And you also see this notch effect where the tip edge of the gears come into contact with the foot root of the meshing gear. So this is for the load distribution. The pressure distribution looks quite similar, and you also get the contour plot where you see where the critical areas along the tooth lengths are. In the Workbench 7.0, we have also this 3D diagram where you can see the pressure distribution or the sliding speeds or the micro pitting safety and so on. And we have also a recommendation based on a very simplified method of SIG, which is based on an ARGMA paper of the 1960s, which still gives good starting points for the evaluation of a tip relief when you are starting from scratch. We can have a look at the flash temperature distribution and on the local micro pitting safety, where we see due to these high pressure values in the foot root and also in the tip, we have micro pitting safety lower than 1. And we can have a look at the maximum stresses in the foot root along the face width. We will talk later a little bit about that when I apply a notch in the foot root. And we have a first result for the vibration excitation or the noise excitation. So here we have a fluctuation range of the transmission error of 1 micron, and we can also have a spectrum after Fourier analysis of this curve. So you see which order has the most influence on the transmission error, and usually it's the first order. And here, to have a complete overview of the gears, you also see the tooth form, the tooth profile, and the microgeometry which we have applied on the gear. So you see we have the helix angle modification in combination with the end release, and still we have no profile modifications. And if you are familiar with the Fva Workbench, you would expect that you would see also the results for the output stage. In the new version, you have the choice that you when you click on the input stage with the right mouse button and you click on Eigenschaften in German or properties in English, you can activate or deactivate this checkbox. So here the input stage will be shown in the report, and when we click on the output stage, you see I've deactivated this checkbox, and then you can focus if you are just working with in this case with the input stage. You can deactivate the display of the results of the output stage. So yeah, you get it's not so it's much easier to find the results which are working with, and you get not confused with results from other stages. Okay, just let's have a look at the result of the load distribution again. So what we have to define now is a profile modification. And and with this profile modification, we want to get rid of these load peaks here. And for this, I want to have a look at the recommendation from SIG. So the recommendation of SIG would be to reduce the 12 to 17 micrometers to reduce the load and pressure values at the begin and end of the mesh to 0. In this case, I do not want to reduce it to 0, but we can have a little bit more load also at begin and end of the mesh. So I start with 5 microns, for example, and I want to apply on the pinion and on the gear wheel a tip relief of 5 microns. And this is done here. So yeah, at yesterday I have implemented 10 and the long tip relief, and so 5 and also a long tip relief, and then we recalculate this. And now we have again a look at the output. And now you see we have some small peaks here at begin and end of the mesh, and but the load distribution, pressure distribution is much better, and therefore I want to avoid those load peaks as well. So I change to a higher value for the pinion and for the wheel tip relief to 10, and do a recalculation of that. And then I want to rename this as width modification. And now I want to do another calculation without these modifications to compare both variants. Then I rename this snapshot as well. Say no modification. This would be the reference and this the comparison. Okay, you see we do not have changed the basic gear parameters, but we have optimize the phase load distribution. And in the Fva Workbench, if you do load capacity calculation according to ICE or DRN, you have the choice to automatically take into account this KH beta value, which is calculated in the system calculation. Then you see which lead modification we have applied. This was the original recommendation. And then you see the difference. Here we had high load peaks, and here we got rid of those load peaks. And also, when we look at the pressure values, we have a quite good distribution of the pressure values without any local load peaks, which we have seen here without any tooth modifications. And yeah, you see this also in this nice 3D presentation. And then we can have a look at the flash temperature distribution. And yeah, you see, because we have no real limiting value for the flash temperature, here everything is red, but the scale of the diagram is half the scale of here. So that's much better or much lower temperature compared to here. And also the local micro pitting safety is much better. So due to the mainly the profile modification we have applied, we have reduced the local pressure values in the foot root of the pinion. This is usually where the micro pitting occurs to the negative sliding, and you see we got rid of this low micro pitting safety values. And then we'll have a look at the distribution of the maximum stresses in the foot root. And here you see the influence of the uneven load distribution. And so we have reduced the maximum stress values a little bit. But yeah, in this case, it's not a significant change, but we have changed it a little bit, and we have also reduced the transmission error from 1.26 microns to 0.8. This sounds not very much, but it's 60% or something. Okay, then we can compare the tooth form due to the micro geometry we have applied. And next thing is I want to show you how we take into account notches in the foot root. And to produce a notch, I will change the manufacturing of the gear tooth. So here the gear tooth the gear teeth have been generated by only one tool. And I implement a second tool, which is called here grinding tool, which I have predefined. And I want to remove, I don't know, 0.2 millimeters. So this is the machining allowance, the value which is grinded off by the grinding tool. And then we can have a look at the tools as well. So the hobbing tool was a very simplified tool, just addendum coefficient of 1.4, a dedendum coefficient, and tip radius coefficient. And I just have duplicated the hobbing tool, renamed it, and then what I've changed is I have reduced the addendum coefficient. So I have reduced the height of the tool, so we do not grind so much in the foot root, and for this, we can generate a notch in the foot root radius, and I have reduced the tip radius of the tool to a sharp edge, so we see a better effect due to the notch. And then I just recalculate So maybe I stop this. I wanted to compare the results. I save this in the workbench model. So I have activated that only 4 snapshots will be saved during the calculations, and the 5th one, if I produce the 5th variation, the oldest snapshot will be deleted. But to save this, you can save it in this section, and then it's also stored within the workbench model, and you can have access to it when you open up the model again next week or so. And then I want to reactivate the tooth modifications, and I think that's not the right one. This is the right one. Yes. And then I do the comparison calculation. And here you see you will get a warning that now you have a notch in the foot root, and then you can decide if this notch is critical or if it's not critical, and that's then your decision. But for this, you have to have a look at the stress values in the foot root. So I call this with mod notch, and then I want to compare this with the first calculation, and then here we focus only on the tooth root stress calculation results. So all the other results, we already had a look at that. And now when you look at the scale of the stresses, here we have the highest stress of 221, and here we have the highest stress 250, and this is exactly the influence of the notch. And we also have minor changes in the transmission error because we have changed a little bit the tooth geometry to the second tool, but that is not a significant change. But there is a change in the tooth geometry. So, and if we would have again a look at the micro pitting calculation, so we have the influence of the speed because speed is a big influence factor on the thickness of the oil film. And of course, we have influence of the load, as we have seen here. When we reduce the high local load peaks, then we have a higher micro-pitting safety. But also the oil quality is a big influence. And this can be influenced by the definition of the oil. So when I click on the lubricant, which I've chosen, there was a damage load stage of 9 for this oil, and if I reduce this to a very low micropitting capacity of the oil, we can recalculate this as well, and then we will see that we have again much lower micropitting safety values. Okay, then I set this as a reference because here we have the actual geometry and the tooth modification, and I compare the new calculation with the reference. And then you will see that now the micropitting safety here everything is red with micropitting safety values lower than 1 just by changing the oil quality. Okay, the last variation I want to do is that we have a look for the load distribution when we have, for example, very high startup loads. So I click on the gearbox here and change the power from 180 to maybe 360 or 400 if we have a big motor which produces high startup torques. And then I want to see how is the load distribution for this condition. And now we will see we are getting to critical values at this position here for this very high load. And usually I compare now the stress values not with the fatigue limit, but with the static strength of the material, which is for case hardened gears around about 2,400 megapascal. And you see we have here at the very highest point 2,500. But again, this is can be discussed if we should have a look at these values. But here you see we have a lot of values with up to 2,000. So I would say if we neglect this one singularity, let's say it like this, then I would not expect a pitting failure due to these high startup loads in this region, because we have the stress values lower than the static safety of the tooth flank. And the last variation, we could do it the other way around. If we have low load conditions, maybe we run only with 50 kilowatt, and then we can have a look at the contact pattern if we still have enough contact over the whole tooth flank. So here the pressure values are not critical because we have very low loads, but yeah, maybe we lose the contact ratio, and this can also be seen then in the calculation. Of course, we have high KH beta values, but due to the low load, this is not a problem. And yeah, we have here a smaller contact pattern, but we think we still have enough overlap ratio. Okay, so this was the presentation from my side about the capabilities of the Fva Workbench, talking about the local load capacity calculation. So do you have any questions about that? Christine, is that could the participants ask the questions? Are there?
No, there are no questions at the moment.
Okay. Okay. So if there are no questions, then I thank you for your time. I hope you have seen a little bit new in the Fva Workbench. And if you have any questions about the calculations or the new version of the Workbench, please don't hesitate to contact us, or you go to our social media accounts and look for all things which are new. So then I wish you a nice afternoon and goodbye.